Alright, so now it's the time to apply the concept of limit to the study of functions. So this is section 2.4, limits and continuity. Something you may have heard before is that functions, in a sort of heuristic way, is that functions that are continuous are those functions whose graphs have no breaks. Okay, so if you have a function like this, you see that it's kind of nice. The graph doesn't seem to break anywhere. This is the first graph portrays a continuous function everywhere, and this is a function that is not continuous when I'm about to draw. So there's a break here, another one over here. So this function here is not continuous at 2 points. But that's just an intuitive notion. No, it's not a formal statement, and here we're doing mathematics, so we'll try to formalize what this is. Now, the motivations behind come from several phenomena. I mean, you create math in order to apply it to problems coming from the real world. At least when you first develop a theory, you have something in mind. And for instance, most quantities that people care about, so for instance, velocity, temperature, etc., are continuous functions. So if you were driving a car, you cannot just go from going at 30 miles per hour to close to the speed of light in 1 second. That's not physically possible. And even when there's a car crash, even though there's a sudden change in velocity, that actually is not instantaneous. So there's no break in reality. So this is just something that happens very quickly, and there's it's something that would seem to, it would look like a almost vertical asymptote, but it's not. It's just a very sharp turn. The function still continues. And changes in temperature also throughout the day, you see that you go from 1 degree to the next, and even though you may go up or down a little bit faster, a little bit slower at times, but it's still a continuous transition from one point to the next. And so when you study these things, it is useful to have the notion of a continuous function and to formalize this concept. And so if we want to talk about continuity, we first need to discuss what's the continuity at a point. So first, let's assume that f of x is a function that is defined on an open interval containing the point x equals c. Then we say that the function is continuous at the point c at x equals c if the limit of f of x as x goes to c is equal to f of c. This statement here is this statement here is made of actually three separate statements, and it actually encodes a lot of information. So as we'll see, we'll summarize this next. But you see, this formula here assumes that the right-hand side is a number, so it's well defined. So the function f takes in a value at x equals c. When we're looking at or introducing the notion of limit, we didn't care about the value of the function at the point c, and the function may, I mean, in some of the examples we covered, the function was not even defined at the point. So here we're requiring the function to be defined and to be defined, and also that it equals the limit of f of x as x tends to c. So that means also that the limit exists. So for a function f of x, the limit may not exist when you approach a number. We're actually requiring that this limit exists. And the third statement is that the limit and the value of the function at the point are the same. So three things need to hold. And if any of these conditions fail, then we say that the function is not continuous at the point. So say the limit does not exist. That's one possibility. Or if it does exist, but is not equal sorry, to f of c, we say that f has a discontinuity or that is discontinuous, which is what I was about to write first. Discontinuous at x equals c. And so, as we were saying before, for f to be continuous at x equals c, the following must hold, the following conditions, the following needs to happen. One, we need that f of c is defined. So there's a value assigned to c. and by the function, and then the limit of f of x as x approaches c exists. 3, they are equal. Okay, so these are the three conditions that are necessary in order for a function to be continuous at a given point. Now, you can also take a look at the second statement and think of it as it can be broken into two separate statements also. Into three separate statements also. The first one is that the limit from the right exists, the limit from the left exists, and they're equal to each other. So that would imply that the limit of f of x as x approaches c exists. So there are a lot of things here in this to consider in this formula over here. This simply looking formula here is something that encodes a lot of information about a function. So that's why it's not immediate that a function will be continuous at a point, because there are a lot of things that need to happen in order for that to be the case. Now that we've introduced the notion of continuity at a point, we say that f is continuous at all points in an interval. So if f is continuous at all points inside an interval I, then f is said to be continuous on I, on the interval I. Now we need to separate a case when we have a semi-closed or closed interval, so if we're including the endpoints. So if f is defined on an interval of the form AB or just AB, so when we're including A as a left endpoint, we require that the limit of f of x as x approaches a plus is equal to f of a. To say that the function is continuous there, we want that. So suppose that we have a function that's defined on this close, semi-closed interval, so it's open here, so you don't include b, but you include a. So here we don't have any value assigned to the point b, the function is not defined there, so it's a function f of x, but here we do. So this is f of a. So here we can compute the limit as x approaches a, but from the right. On this side, f is not defined, so it doesn't make sense to speak about the left-hand limit. And so that's the only thing that we require, that limit from the right of f of x as x approaches a is equal to the value of f at that point. And now similarly, this is completely analogous. If I includes b as a right endpoint, then we must have that the limit of f of x as x approaches b minus is equal to f of b. Finally, so we want to speak of continuous functions, period. But in order to do that, we introduce the notion of continuity at a point. So the natural notion here is that we'll say that if f is continuous at all points in its domain, then f is called just continuous, simply continuous. If you talk about a continuous function, that means that it's continuous at every point inside the domain. Okay, so let's look at an example you must be very familiar with now. I mean, at least those of you who have taken pre-calc and algebra. Probably one of the first nonlinear functions that you ever encounter in your mathematical studies. So let's look at the function f of x equals x squared. This function is actually continuous. Yeah, the function is continuous. This is what we get when we try to draw the graph of a quadratic function. So this is f of x equals x squared. So let's pick any number in its domain. The domain of f is R, so all the real numbers. Let's pick a number c, and we see that f of c is c squared, because that's the rule that tells us what to assign to each number x. We just take that number and raise it to the squared. So this height here is c squared. And if we approach c from the right, you see that the values of y, so the values of x squared, approach c squared. The values that are decreasing towards c squared. And the same thing happens when we approach c from the left. The values of f approach c squared. It's just that the values are slightly smaller than c squared. So we know that f of c is equal to c squared, so that's one thing. Now we also know that both right and left hand limits agree, so the limit exists. So the limit of f of x, and no matter what is the value of c, this is what will happen. So the limit of f of x as x approaches c is the limit of what? The limit of x squared, because that's what f of x is equal to as x approaches c. And this is, well, we can use the product law. Both limits exist, so we have limit of x, and when x approaches c, well, x is approaching c by by assumption. So this limit is c, this limit is c over here, so you get c squared. And so this limit is actually equal to the value of the function. So conclusion here is that since f of c is also equal to c squared, and limit of f of x comma limit of x is equal to c is equal to c squared. Now exists first, and its value is equal to c squared as well. F is continuous at c. But the point c is arbitrary, so we might as well have been checking this for any point. So the conclusion is that f is continuous because it continues at every point in its domain. Okay, so we've checked all the properties that we need to check in order to show that the function is continuous at a point. And since the point we chose is just a generic C, we've actually shown at once that f is continuous at every point in its domain. That means that the function is continuous. We next continue with some examples that show what could go wrong when we talk about discontinuities.